everyone, in this video I'm going to summarize this paper titled Adaptive Fractional Order Sliding Mode Control for Robust Frequency Regulation in Islanded Renewable Microgrids, so you can understand exactly what this research does without reading the whole thing yourself. Let's start with the abstract. This paper deals with a real problem, keeping the frequency stable in islanded microgrids that rely heavily on renewable energy. These systems have low inertia and constantly changing disturbances, which makes traditional controllers either too slow, too aggressive, or too noisy. The authors propose an adaptive fractional order sliding mode controller that uses memory-based dynamics, an online disturbance estimator, and a genetic algorithm for tuning. The results show over 80% reduction in chattering and much smoother, faster frequency regulation, tested both in simulation and on real hardware. Now let's go through how they built and proved this. This is the overall structure of their proposed method. The measured signal goes into a fractional order switching surface. An adaptation law estimates the disturbance in real time, and the genetic algorithm optimizes the controller offline until the response is optimal. Here is the microgrid they tested it on: wind, solar, fuel cell, diesel generator, flywheel, and battery storage, all connected and coordinated through a distribution management system. This diagram shows the mathematical block model of that microgrid, how each power source fits into the frequency deviation output. And these are the actual disturbance profiles they used: wind, solar, and load, all changing over a 300-second simulation to stress test the controller. This table just lists the system parameters used in the simulation: time constants, gains, and inertia values. Next, this shows the genetic algorithm optimizing the controller gains. You can see the fitness value stabilizing after about 12 generations. And these are the final optimized parameters that came out of that process. Now here is the key comparison: frequency deviation and power outputs under disturbance compared across PID, classical sliding mode, a reference fractional method, and their proposed controller. Their method shows the smoothest response with the least oscillation. This table backs that up numerically. Their method has the smallest overshoot, undershoot, and by far the lowest chattering index. Let's look at the actual control signals sent to the generators and the storage units. Classical sliding mode produces huge, unrealistic spikes, while their method stays smooth and practical. Numerically, chattering in the control signals drops by 70 to 85% compared to the other methods. This shows the sliding surfaces themselves. Their controller reaches and stays on the surface smoothly, without the oscillations seen in classical sliding mode. Same story here: chattering reduced by orders of magnitude. This is the adaptive gain over time. It rises right after each disturbance to compensate, then settles back down, which is exactly the behavior you want. Now let's move from simulation to real hardware. They validated everything on this real-time hardware in the loop setup, using a SpeedGoat target machine connected to a host PC. And here are the real-time results. Frequency deviations stay tiny and recover quickly after each disturbance, confirming it works outside simulation too. Finally, the control signals from the real-world test stay smooth and within reasonable limits, just like in simulation. So overall, this paper shows that combining fractional order dynamics with adaptive disturbance estimation and generic tuning gives a controller that's both more robust and much smoother than existing methods, and it actually works in real time, not just on paper. I'll be covering more papers related to this topic soon, so stay with us.